Now that we've done some basic problems with Coulomb's law here, we're going to move into situations where there's more than just two charges, and we're going to have to think about all the forces, all the combinations of forces between every pair of charges. So what we're going to do is really just an extension of what we've been doing, and that is we're going to calculate the force from each individual charge or from each individual pair, and then we're going to add those forces up, of course being careful with our signs. Remember, we just take the magnitude of the charge when we're actually doing that calculation of force, and we're going to use that sign to determine the direction. And the last thing is we're going to bring back vector addition, adding components, something that we did a while ago, a lot during the forces unit, not as much recently, but we are going to bring back that idea because that's going to matter here for certain problems when it's in 2 dimensions. For this problem here, we have 3 charges in a line. Charge 1 here has a charge of negative q, charge 2 is negative 2q, and charge 3 is positive 2q. We want to determine the net force and direction of the force on each charge. So I'm going to start by simply identifying the forces that I have. So I'm going to start with charge 1 and 2 and look at the interaction between those two. And since they're both negative, they will repel, so they're each going to exert a force on each other, repelling it. And so I'm going to call that force F12, the force between 1 and 2, and you see they're both going away from each other. Then I'm going to think about 1 and 3, and so these two charges have opposite signs, so they will attract. So that means there's going to be an F13 here going to the right on charge 1, and an F13 going to the left on charge 3. Lastly, we're going to think about the interaction between 2 and 3. They also have opposite signs, so they will also attract. So that means F23 here is going to be going to the right on charge 2 and to the left on charge 3. Now that I've identified the direction of those charges, I'm going to use our equation, Coulomb's law, to determine the amount of force that we have. So F12, the force between 1 and 2, is going to be K times charge 1, which is just Q. Remember, we're ignoring the signs and just thinking about the magnitude, times charge 2, which is 2Q, all over the distance between them, which is D squared. And so that ends up being 2 times KQ squared over D squared when we go ahead and simplify it. For the force between 1 and 3, that's going to be K times charge 1, which is Q, times charge 2, which is 2Q, all over the distance between them, which is going to be from here all the way to here. Alright, so that's actually a distance of 3D, and that quantity is squared, so we end up getting 2 times KQ squared over 9D squared, because we have to square the 3 as well. And finally, for the force between 2 and 3, we have K times 2Q times 2Q over the distance between them, which is 2D, that quantity squared. So we end up getting 4KQ squared on top over 4D squared on the bottom. Those 4's cancel out, and it just simplifies to KQ squared over D squared. We're now going to combine these forces to figure out the net force on each charge. So starting with charge 1, we have F13 going to the right and F12 going to the left. So I'm just going to add these two forces that I solved for down here, being careful with my direction, of course. So F13, since it's going to the right, I'll say that's the positive one. So we have 2KQ squared over 9D squared minus that F12 going to the left. Okay, you could have flipped the signs, but I'm going to go with the standard convention. I need to make this have the same denominator, so I'm going to multiply top and bottom by 9. And then when I go ahead and combine those two, I end up getting negative 16KQ squared over D squared. So the magnitude of the force is just going to be 16KQ squared over D squared. But because it's negative, that means this force is going to the left. So there's the net force on charge 1. Moving on to charge 2 here, I'm going to be combining F12 and F23. So F12 is going to be 2KQ squared over D squared plus F23, which is KQ squared over D squared, and those end up becoming 3KQ squared over D squared. Since it's positive, the direction of that force is going to be to the right. Lastly, I'm going to combine the two forces acting on charge 3 here. So that's F13 and F23. So F13 is 2kq squared over 9d squared, and since it's going to the left, I'm going to make it negative, plus the force between 2 and 3 also going to the left, so I'm also going to make that negative, kq squared over d squared. Once again, I'm going to find a common denominator here by multiplying top and bottom by 9. And when I add those two together, I end up getting negative 11kq squared over d squared. So the magnitude of the force is just 11kq squared over d squared. And its direction is left because it's negative, and that's the direction that I set to be the negative direction. Okay, for this next one here, we want to calculate the magnitude and direction of the net force on the top right charge, this one here. So I'm going to once again label these charges 1, 2, and 3. And I'm going to think about the forces, and I really only care about the ones on the top right. So on the top right, that's going to be attracted to this force here on the left. Call that F12. And then the top right and bottom right forces or charges are going to repel each other because they're both negative, so we're going to have F23 going up like that. I'm now going to use Coulomb's law to go ahead and solve for the amount of force that we have between each pair of charges. And so starting with F12 here, we're going to have K, which is 9 times 10 to the 9th. We'll actually enter numbers here, times charge 1, which is 4 millicoulombs. Keep in mind that milli is a prefix that means 10 to the negative third, so 4 times 10 to the negative third coulombs, times charge 2, which is 3 times 10 to the negative third, because it's millicoulombs as well, all over the distance between them, which is 2 squared, and end up getting a force here of 27,000 newtons. I'm going to do the same thing here for F23. And so that's going to be 9 times 10 to the 9th. Once again, the two charges now are going to be charge 2, which is 3 times 10 to the negative third coulombs, and charge 3, which is 6 times 10 to the negative third coulombs, all over the distance between them, which is also 2. And for that one, I get a force of 40,500 newtons. Now that I have those two forces, I can go ahead and combine them. I notice that they are at right angles. Okay, so I don't necessarily need to break anything into components, but I do need to combine the X force and the Y force. So this one actually saves us a step because we don't need to componentize anything, but we do need to put together these two forces, the 27,000 newtons going to the left and the 40,500 newtons going up, and we're going to solve for that hypotenuse, and we're going to solve for that angle. So in order to get that hypotenuse, I'm going to use my Pythagorean theorem. A squared plus b squared equals c squared. So 27,000 squared plus 40,500 squared equals c squared. And I get a hypotenuse value here of 48,675 newtons. Okay, so that's going to be my magnitude. And for the angle, I'm going to say that tangent of theta equals opposite over the adjacent. So that means that my angle here is going to be the inverse tangent of my opposite side, which based off of how I have the angle is 40,500 over the adjacent side, which is 27,000. And I end up getting an angle here of 56.3 degrees. So putting all of this together, all right, our net force, the magnitude of our net force, is going to be 48,675 newtons. And the angle, or the direction, is going to be 56.3 degrees north of west. Of course, as always, you could solve for the other angle, in which case it would be 33.7 degrees west of north. And just as a quick refresher here, obviously in the last problem we used some vector addition. If you do need a refresher on some of the basic steps, here they are. The first thing we're always doing is breaking up our forces, any vectors at angles, into their components. Going to componentize the vector. Once we have them broken into components, we're going to add up the x and y components separately. In the case of the last one, they already were separated into x and y, so we got to basically skip those first two steps. We're then going to put back those two components together, the sum of the x components and the sum of the y components, and use trig and Pythagorean theorem to find the magnitude and direction of that resultant force.